Okay, so good evening. I welcome you all to this week 10 session, and let's start with a recap of week 10 session. So as I mentioned, this was the last week for filter designing, and which included FIR filter designing. So we know that FIR is finite impulse response filter designing, and we looked at the windowing technique for that. And in this week we looked at different types of windows. So the first window which we looked at was this rectangular window, which we had been looking in the last week as well. Then we looked at the triangular window. After that, a new window was introduced, which was Hanning window. And this Hanning window has an equation as in time domain as W of k is half of 1 plus cos 2 pi k by 2n, and this k will be from minus n less than or equal to k less than or equal to n. This is Hanning window. Then we had Hamming window, and this Hamming window was wk, which was equal to 0.54 plus 0.46 cos of 2 pi k by 2n. Then we had this Blackman window. This Blackman window had its response as wk equal to 0.42 plus 0.5 cos of 2 pi k by 2n plus 0.08 cos of 4 pi k by 2n. And then we had this Kaiser window, and this thing has response as wk equal to I naught, which is Bessel function beta n under root 1 minus k by n square upon I naught beta n. So this we had looked at. After that, this relation between windows and Gibbs phenomena was discussed. Then we had compared the FIR and IR filters, and after that we went on to the new topic, which was realization of causal rational filters. In that we introduced signal flow graphs and pseudo assembly code. In signal flow graphs, or rather for this realization, we looked at two different kinds of realizations. I think one was direct form 1 and one was direct form 2, I think. Yes, and we shall be continuing with the same thing in the coming 11th week as well. So let me quickly start with the questions that I had planned to cover today. So let's start with the first question. So these are last year assignment questions, and the first question says that a rectangular window sequence takes value 1 when 0 is less than or equal to n, is less than or equal to 5, and 0 otherwise. What is the Fourier transform of this sequence? So this is a simple question. It says that I have a window, let's say W of n, and this is 1 for 0 less than or equal to n less than or equal to 5, and it is 0 otherwise. And we need to figure out the Fourier transform of this. So let's say the Fourier transform, or rather DTFT, of this quantity be capital W of omega, and therefore this W of omega is equal to summation n running from minus infinity to infinity W of n into e power minus j omega n. So now we know that this W of n is 1 between n equal to 0 to 5. So from n running from 0 to 5, we have this as 1 into e power minus j omega n. So we have here summation n equal to 0 to 5 into e power minus j omega n. So now we know that this is a geometric progression, finite geometric progression. With first term as 1 and common ratio as e power minus j omega, and number of terms as 6. So therefore, this W of omega is first term into 1 minus e power minus j omega to the power number of terms divided by 1 minus common ratio. So this W of omega is 1 minus e power minus j omega 6 upon 1 minus e power minus j omega. Now in order to write it in some good form, what we can do is we can just take common e power minus j omega 3 outside from numerator. Then here we will be having e power j omega 3 minus e power minus j omega 3, and from the denominator we can take out e power minus j omega by 2 outside. Then here we will be having e power j omega by 2 minus e power minus j omega by 2. So this thing now becomes e power minus j omega 3 minus half will be 2.5. Then in numerator and denominator I can just divide by this 2j, nothing will change, and this quantity here is simply sine of 3 omega, and similarly this quantity here is sine of omega by 2. So now we are left with sine of 3 omega upon sine of omega by 2. So therefore for our given window function, this is the Fourier transform. Any questions in this? Okay, if there are no questions, then let me move on to the next question. So the next question says that we have to design a high pass filter with FP, that is passband edge, as 300 Hz and Fs, that is stopband edge, as 200 Hz, which exhibits attenuation greater than 40 dB in stopband. We need a passband ripple to be less than 0.2 dB, that is passband tolerance. We assume that the sampling frequency to be 1200 Hz, and the limits in the passband and stopband attenuation correspond to the magnitude response and not magnitude squared response. And now we need to figure out the approximate window length if a Hahn window is designed. So let's just write down whatever we are given here. So we have this passband edge FP as 300 Hz. Now this is analog, so we'll just convert it to our digital thing, that is omega p, which will be 2 pi fp upon f sample, which is 2 pi 300 upon 1200, and this comes out to be equal to pi by 2, and we have fs as 200 Hz, which will give us omega s as 2 pi fs upon f sampling, which will give me 2 pi into 200 upon 1200, and this comes out to be equal to pi by 3. Now what we need to find out is, we need to find out the approximate window length if a Hanning window is used to design this filter. Now if we look at Hanning window, so in the lecture we had discussed that for a Hanning window, the main lobe width is given by 4 pi by n, and for that window where this window belongs to minus n to n, like in this region this window will belong, window is for k running from -n to n, that is, which means window length is 2n plus 1, and we need to find out this. Okay, so for a Hanning window, we know that the main lobe width is 4 pi. Another thing that we had discussed is this main lobe actually gives us, after having convolution in frequency domain, this actually gives us the transition width. Transition width or transition band width. Okay, and what is this transition width? Let's say I denote it by omega t. So this omega t, which is transition width, is basically my difference between my passband and stop band edge. So here I am having a high pass filter. So my high pass filter will look something like this. So this thing is my omega p and this thing is my omega s. This is my high pass filter. So this region, this shaded region, yellow shaded region, is basically omega t. So this omega t is given as this omega t is the difference between the high pass cutoff and the stop band, the pass band edge and the stop band edge, that is omega p minus omega s. Now this omega p we had obtained as pi by 2 and omega s we have obtained as pi by 3. So this will be equal to pi by 2 minus pi by 3, and this comes out as pi by 6. So now what we know? We know that my omega t is pi by 6, and we know that this transition width translates to, or rather this main lobe width translates to transition band width, which means that this transition band, that is omega t, should be approximately equal to 4 pi by n. So now we can say that this transition width, that is omega t, should be equal to main lobe width of Hanning window so therefore this omega t should be equal to 4 pi by n. Therefore my n should be equal to 4 pi by omega t, and this omega t we have obtained as pi by 6. So we have this as 4 pi upon pi by 6. This pi gets cancelled and we have this 6 into 4, which is 24. Now this is the value of n, but the length of window is not n. Length of window is 2n plus 1. So therefore length of window is 2n plus 1, which is 2 into 24 plus 1, which is equal to 49. Is this point clear? Is this question clear? Any queries here? Any questions in this particular part? Okay. If there are no questions, then I'll move on to the third question now. So yeah, the third question is somewhat filter designing. It's not too involved, just a small question. So it says that we have a band limited signal 160 kilohertz and passband and stop band tolerance in magnitude is 0.15, and sampling, we have an ideal sampling at 330 kilohertz. So this is the exactly same data which we had used to design a band pass filter in last week. that is week 8. Same data, and transition band is 4 kilohertz on either side of the pass band. And we need to use Kaiser window to design an FIR filter. So the first question is, what is the value of minimum stop band attenuation parameter A in Kaiser window? So for Kaiser window, this A is equal to minus 20 log delta to the base 10, where this delta is attenuation, and so this is stop band attenuation, and for us this delta is given as 0.15 in magnitude. So this thing is equal to 0.15. Therefore, A is equal to minus 20 log 0.15 to the base 10. And if you use your calculators, this comes out to be equal to 16.478 dB. This is a simple question. Still, if you have any queries, then let me know.
Madam,
Sorry, any questions?
that is not attenuation, it is tolerance, no?
Same thing, sir.
Yeah.
In stop band,
Yeah,
this is the thing, na?
yeah,
So
that's
this
one.
this is tolerance only for
Yeah,
stop band because it starts from 0.
yeah. Okay.
Yeah, that thing will come into picture when you're having a pass band thing. But this is in stop band, so it's fine. Yeah. Okay. If there are no further questions, then I'll move on to the next one. And now we need to, in this question, we need to find the shape parameter, that is beta, for the Kaiser window. So now this shape parameter, so we had seen that we define another variable which is alpha, which is beta into n, and which implies that my beta will be alpha by n. So this is the first thing that we are having, and this alpha will depends on the value of uh, what value of A we are having. So this has 3 ranges. So this alpha is equal to 0 if A is less than 21. It is equal to 0.5842 into A minus 21 to the power 0.4 plus 0.07886 into A minus 21 for for 21 less than or equal to A less than or equal to 50, and this thing is equal to 0.1102 into A minus 8.7 for A greater than 50. And in the last question we had found out this A, so this A is 16.478. So we have A as 16.478, which is less than 21, which means that alpha will be equal to 0, which also means that beta, which is alpha by n, will also be equal to 0. So now we have the value of beta, which is the shape parameter. So now we have A, we have alpha or rather beta, and the only thing that we need to figure out is the value of n, which is related to the order of the filter. So next we need to find out the minimum value of n. And for this Kaiser window, n plus 1 should be greater than or equal to 1 plus a minus 8 upon 2.285 omega t, where omega t is transition width and we know that this ft in the data which is given to us, this ft is 4 kilohertz on either side of passband, means the transition width is 4 kilohertz and the sampling frequency is 330 kilohertz. So then we have ft as 4 kilohertz and we have f sampling as 330 kilohertz. So therefore omega t will be equal to 2 pi ft upon f sampling, which is equal to 2 pi into 4 kilohertz upon 330 kilohertz, and this comes out to be equal to 0.024 pi. Okay, so now we have the transition width and now we can substitute this particular value in this equation. So the equation that we are having is 2n plus 1 should be greater than or equal to 1 plus a minus 8 upon 2.285 omega t. So this is equal to 1 plus the value of a we had obtained was 16.478 minus 8 upon 2.285 multiplied by 0.024 into pi. And if we solve this using calculators, this comes out to be equal to 50.209. So therefore 2n plus 1 is greater than or equal to 50.209. We need to find out the value of n. So this n will be greater than or equal to 50.209 minus 1 upon 2, which is equal to 24.60. So if n is greater than or equal to 24.60 and n has to be an integer, then the smallest possible integer that we can take is 25. So therefore smallest value of n is 25. Is it clear? Is it okay? If you have any questions, then let me know. Okay. If there are no questions, then let me just move on to the next question. So this question says that we need to find the number of adders, constant multipliers with gain not equal to 0 and 1, and unit delay buffers required to realize h of z using the signal flow graphs of direct form 2. Okay, so this is what we need to find out. Okay, so let's start by doing that. So we have this h of z, which I can write as y of z upon x of z as 3 minus z inverse upon 1 plus 2z inverse minus z to the power minus 3. So now I can write this as y of z into 1 plus 2z inverse minus z to the power minus 3, which is equal to 3 minus z inverse into x of z. So if I take inverse z transform, then this becomes y of n plus 2 times y of n minus 1 minus y of n minus 3, which is equal to 3 into x of n minus x of n minus 1. So from this equation, we have y of n as 3 into x of n minus x of n minus 1 plus minus 2 y of n minus 1 plus y of n minus 3. So in direct form 2, we first realize this part and then we realize this part, and then by using the combined delay thing. So let's start with realizing this part first. So we are having this thing here. Yeah, this is x of n, and this is some pseudo y, so we'll have a z inverse here. Then this gets multiplied by a gain factor of minus 2. Then a z inverse is here. Now if you observe here, this is y minus 3, so there is nothing getting multiplied here, so this will remain as it is. Then to get y minus 3, I'll have z inverse, and this thing gets multiplied by a gain of 1, and this gets added with this gets added with this, and we have this thing here. Now here we have, first we have 3 times x of n, so this will be a gain of 3, and after a z inverse I'll have a gain of minus 1. This will get added here, and then I'll have my y of n here. Okay, so this representation here is direct form 2. And if we observe, then we have the transfer function h of z as 3 minus z inverse upon 1 plus 2z inverse minus z to the power minus 3. Now if you observe carefully, when we are doing a direct form 1, so if you can just skip all of these steps, and what you can do is you start with the denominator. So first you have a 1, so you will have a gain of 1 coming here. Then you have 2z inverse, so you will have a z inverse here, and then this z inverse will get multiplied by minus 2. So if you have a plus 2 here, then you will have a minus 2 here. You will multiply it by minus 1. And why is it so? Because you will be taking all these values corresponding to y of n minus 1 or y of n minus k for k greater than 0 to the right hand side or to the other side along with x's. So if it was positive in this side, which would come from this end, so now when you shift it to the other side, it will become negative. So simply you have a positive sorry, yeah, you have a positive 2 here. If you take it to this side, it will become a negative 2 here, and then you have a minus 1 here, so that will become a plus 1 this side. So then you will have minus 2, then you have say z to the power minus 3 means 3 unit delay. You already have 1 unit delay, then 2 and 3 unit delay, and then you will multiply it by a factor 1. Okay, so this you have for, and then you will just add all of them. Then you have the numerator part. So in numerator part, first you will multiply by this 3, so your x of n. So then you will multiply it by 3, and then you will add a unit delay, and then you have a gain of minus 1. So you will multiply it by minus 1 and then add it like this. So just by observing the transfer function, you can draw this thing. There is no need to just do these calculations and other stuff. Okay. So this was the direct form 2 for this particular question. Now what actually is asked is, we need to find out the number of adders, the number of constant multipliers with gain not equal to 0 and 1, and the number of unit delay buffers required to realize this function. So let's start with the number of adders. So if you observe, so when we are having adder, 2 branches should be coming to that node, and 1 branch should go outside. 1 or 2 branch should go outside. Okay, so there should be 2 branches coming inwards. So if we look at this particular node here, we have this branch coming in and this branch also coming in. So yes, this node will serve as an adder. Then you look at this particular node. So we have this branch coming in and this branch coming in and this branch going out. So again, this at this point we'll be adding this thing and this thing. So again, this is also an adder. Then this node is just a pseudo node. It's not doing anything. It's just like a connector. This is also like a connector. This is also like a connector. Now if you look at this particular node, we have this branch coming in, and then we have 1, 2 and 3 branches coming out. So all the information which is present in this particular branch is transferred to this branch and this branch, which means no addition is getting performed at this particular node. So this particular node is not serving as an adder. Okay, similarly, if you look at this node, we have 1 branch coming here, and then we have 1 branch going out here and another branch going out here. So two branches are not coming inside this particular node. Therefore, this is also not serving as an adder. Again, this particular node is like a connecting node, nothing, it's not doing anything. Now this is the last node that we need to check in. So then we have this particular branch coming in and this particular branch also coming in. So we are having 2 branches that are coming inside this particular node and 1 outgoing branch, which means that this node is again an adder. So therefore we have 3 adders. Okay. After that, we need to look at unit delays. So for unit delays, we can see that we have Z inverse, we have a Z inverse here, and we have a Z inverse here, which means that we have again 3 unit delays. Now for unit delays, you can just look at this transfer function. So this unit delays, see, 3 is the highest order in numerator or denominator. So the highest order which is in numerator or denominator, wherever, so that will give you the number of unit delays. So here we are having z to the power minus 3, that is highest order is 3, and therefore we will be having 3 unit delay. So this argument is there for direct form 1 and direct form 2 only. Sorry, not for direct form 1, only for direct form 2. For direct form 1 you have separate delays. Okay, so you have this thing here, and the last thing that we need to figure out is the number of multiplier units, and this multiplier units should not have a weight of 0 and 1. So if you observe here we are having a branch. So for multiplier units we need to check all the branches for its weights. So here you are having a branch, but here its weight is 1. Then here you have a branch, but now here its weight is 3. So this we should count. Then we have a branch here, again its weight is 1. Here also we have a branch, its weight is 1. Then here we have a branch, its weight is minus 2, so we should calculate it. Then here we have a branch whose weight is minus 1, so again we should calculate it. It's not a unit weight, it's having a negative sign. We need to consider it. Then we have a branch, we have a branch here, its weight is 1. Then these are all z inverse things, so we don't need to look at them. And here we have a branch which has a weight of 1, so we don't need to consider this. So now we are having, so therefore we are having 1, 2 and 3 multiplier units. So we have 3 multiplier units. Is it clear? Any queries in this question? Queries in any question that I have covered till now? Okay. Okay, if there are no questions, then let me move on to the next question that I am having today. Okay, so this is the next question here. Now it says that for the given signal flow graph, give the system function. So this is the signal flow graph given to you. So again, when you are having two incoming branches, you will have an adder there, and otherwise you will just pass on all the information whatever you are receiving to that particular node. So now you need to find out the signal transfer function. Okay, so let's start. So we'll go point by point at every node and see what signal we are receiving here. Okay, so if you look at this particular node, this node is x of n. Okay, then this x of n, if we look at this particular node here, this x of n gets delayed by x1 unit, that is x of n minus 1. And if we look at this particular node here, we'll be having x of n minus 2, because again it is getting delayed by 1 unit here. Okay, now let us look at this particular thing, this particular node. So now here we were having x of n minus 2. This x of n minus 2 gets multiplied by 15. So at this particular location, we will have x of n minus 2 multiplied by 15. So we have here x of n minus 2 but multiplied by 15. Okay, then Let us look at this location. This, I am not saying this location, I am just after this gain block. This location, this one. So at this particular location, we have this x of n minus 1 and it gets multiplied by 10. So we have 10 into x of n minus 1, which means that at this location, that is after addition, I'll be having addition of these two quantities, that is 15 into x of n minus 2 plus 10 into x of n minus 1. Okay, so we have reached at this point, and after that we are passing this information to this particular location. So till this point we are having this particular information. Now here this thing gets added with this thing. So let's say this, at this particular location we are receiving a of n, which is some signal, and this a of n is equal to 8. So this is 8 times x of n plus whatever is available here, which is passed on to this location. So here what is available to us is this quantity, that is 10 into x of n minus 1 plus 15 into x of n minus 2. So we are having this thing here. Okay, so now we are at this location. So this is a of n. So now let us look at this particular part, which is feedback part. So now in this feedback part, this thing here is y of n, and this y of n gets delayed by 1 unit. So that will lead me to this particular location. So at this particular location, I'll have y of n minus 1. Then at this location, well, let me use a different color here. It's too much. At this location, this y of n gets multiplied by 12. So we have 12 times y of n minus 1. And therefore at this particular location, or rather a little bit this side, at this location, what is happening is this a of n is getting added with this 12 times y of n minus 1. So now here we'll have a of n plus 12 times y of n minus 1. And if you observe, this thing is just getting passed to y of n, which means that our y of n is also equal to a of n plus 12 times y of n minus 1. Okay, so the relation that we have obtained now is y of n is equal to a of n plus 12 times y of n minus 1, and this a of n is simply 8x of n plus 10x of n minus 1 plus 15x of n minus 2. So now, and plus 12 times y of n minus 1. Okay, this we are having. And now what we will do is, we will just take all the terms corresponding to y of n, the left side, and we'll keep all the terms corresponding to x of n. to the right side. So we have y of n. So let me just increase marker size. Yeah, we had y of n as 8 times x of n plus 10 times x of n minus 1 plus 15 times x of n minus 2 plus 12 times y of n minus 1. So now we'll take this term to the left hand side. So therefore we have y of n minus 12 times y of n minus 1, which is equal to 8 times x of n plus 10 times x of n minus 1 plus 15 times x of n minus 2. And now I'll just take z transform. So we have y of z minus 12 times z inverse into y of z, which is equal to 8 times x of z plus 10 into z inverse into x of z plus 15 z to the power minus 2 into x of z. So therefore y of z multiplied by 1 minus 12 z inverse is equal to x of z into 8 plus 10 z inverse plus 15 z to the power minus 2. So therefore the transfer function h of z is equal to y of z upon x of z, and this comes out to be equal to 8 plus 10 z inverse plus 15 z to the power minus 2 upon 1 minus 12 z inverse. So this is the h of z that we are having. This is the transfer function that we are having. Any questions till this part? Okay, so this same question, so this is a little bit complicated thing. 1 second, so let me just move this page a bit here. Okay, so this is a long process to do it. So can we just look at this particular figure which we are given and formulate the transfer function which we want directly by observing this particular thing. This whatever I am saying is just for direct form 1. So if you observe carefully, this representation is direct form 1. Okay, so in direct form 1, this particular, the first part which we are having, this part corresponds to x of z, and this part will get multiplied with y of z. Okay, so now what we need to find out is y of z upon x of z, and we'll have some polynomial of z here and some polynomial of z here. So this red thing whatever we are having gets multiplied with x of z, which means that this thing should come in numerator, and whatever is there here gets multiplied with y of z, so this thing should come here which will get multiplied with y of z. Okay, so now another thing that you should look at is, okay, so if I'm having, for example, let me just add one page. So if I'm having this y of z upon x of z as a0 plus a1 z inverse plus a2 z to the power minus 2 upon b0 plus b1 z inverse plus b, let's keep it as it is, this much was fine. So now this part will correspond to numerator as it gets multiplied by z inverse, and now this thing will be like y of z into b0 plus b1 z inverse, which is equal to x of z a0 plus a1 z inverse plus a2 z inverse. And now what we do for realizing this is we plus xz into a0 plus a1 z inverse plus a2 z inverse. So this denominator part is basically corresponds to feedback thing, feedback, and that feedback, since we'll shift it to this side, so the coefficient gets multiplied by a -1, so the sign of that coefficient gets changed. However, for numerator it remains as it is. Okay, so now if when we are looking, or when we are looking at this particular location, we should be careful while choosing the sign. So in the figure we'll be seeing -1, however in my transfer function I should write a plus b1 here. Okay, so now let us try to do that. So this thing is x of z will get multiplied by this quantity, so this thing is 8, only 8. Then we have x of z gets multiplied by z inverse into 10, and this gets added with 8. So then we will have 10 into z inverse. Then we have here z inverse, so here we have z to the power -2. So this x of n, or rather x of z gets multiplied by z inverse into 15, and this gets added with 10 times z to the power -1 plus 8 into x of z. So here we have 15 into z to the power -2. Okay, in similar fashion, now here what we have is, we have a 1 here. So this y of n is not having any sort of multiplication. We are not having any sort of multiplication here. So then we are having y of n. So here it is a single thing. So, and its direction is this side only. So we'll have a 1 here. Then this y of n gets multiplied by z inverse and will get multiplied by 12 in the right hand side. So this thing will be my b1 here, or rather minus b1. So therefore, in order to take this 12, I'll make it as -1. So I'll have -12 z inverse. So if you compare whatever we did with our standard procedure, like this one and this one, whatever we have obtained is exactly the same thing. So instead of repeating the whole process, we can just look at these things, like just by observation we can do it. Yeah, so this you can do by observation. Now in direct form 1, this part will be first and this part will be afterwards. So in direct form 1, same thing you need to do. You just need to look at the coefficients and construct this, nothing else. So if we look at an example here, so let me just copy paste this thing there. This was a signal flow graph which we had for a direct form 1, direct form 2. So we had this thing here, and here this part was for corresponding to x of z, and this part was corresponding to y of z. So this y of z upon x of z will be equal to, so we need, for x of z we need to look at this particular thing, and there is no sign reversal here, so the arrows are in this direction itself. So one more thing, yeah, that you can keep in mind is if we are having a change in direction of arrows, so whatever is going towards y of n, just take it positive. Whatever is going towards x of n, just take it negative. Okay, it is a feedbacking thing, whatever is happening. So now here we'll have an x of z thing here. So here we have a gain of 3, and it's not having any sort of delay, so it's just a normal 3, just a 3 multiplication. Then this x of n, whatever we had here, this thing gets delayed by 1 unit and gets multiplied by a -1, which gets added to this particular location. So then we can write this as minus z inverse. Now in similar fashion, this part corresponds to y of n, and we'll do the same trick. Now here, if you look carefully, there is no gain, so which means that we'll have a 1 here. Then this thing here, y of n, gets delayed by 1 unit and gets multiplied by -2, but it's in opposite direction, or it's like in a feedback loop. So instead of -2, we'll take plus 2z inverse, and then we have this thing, we have y of z multiplied by z inverse, multiplied by z inverse, and multiplied by z inverse. So we have y of z into z to the power -3, and this thing gets multiplied by 1 here, which means that in feedback thing it should get multiplied by -1. So then we'll have minus z to the power -3. And if you compare the transfer function which we have obtained here with the transfer function which we had used to construct this particular signal flow graph, so both of these transfer functions are same. So therefore, by observation, you can simply construct signal flow graphs, and also by observation you can construct the transfer function. It's fine if you don't go through this big process, just practice once or twice for different signal flow graphs, so that this particular method you get a good hand on it. If you have any questions, then please let me know. This was all about this particular question. If you don't have any queries, then I'll move on to the next question. Okay, if there are no questions, then I'll move on to the 8th question today. Just a minute. Okay. Yeah. So now the next question says how many delay un how many sorry how many unit delay elements would be needed to realize h of z in direct form 1, given that, sorry, this is a not n, so an and bm are not equal to 0. Okay, so this much information is given to us. So let us try to solve this question. Okay, so this h of z I can write as y of z upon x of z, which is equal to summation m equal to 0 to capital M b of m z to the power minus m upon 1 minus summation n equal to 1 to capital N a n z to the power minus n. So now I can just cross multiply and write as y of z multiplied by 1 minus summation n equal to 1 to capital N a n z to the power minus n, which is equal to x of z into summation m equal to 0 to capital M bm into z to the power minus m. So therefore this y of z is equal to x of z multiplied by m equal to 0 to capital M bm into z to the power minus m plus y of z multiplied by summation n equal to 1 to capital N a n into z to the power minus n. Now in order to realize this particular part, how many delay elements will be required? So I can write this particular part as x of z multiplied by b0 plus summation m equal to 1 to capital M bm into z to the power minus n. So this particular part here b0, this b0 is not having any delay unit. So this is a scalar multiplication happening. We are not delaying x of n here. However, whenever we are having z to the power minus n for m greater than or equal to 1, then we are having delay units. So z to the power minus 1 will have 1 unit, z to the power minus 2 will be constructed by 2 unit delays cascaded one after the other. So in similar way, so this particular part will not contribute to the number of delays. So this thing here will not contribute to delays. However, this part here will contribute to m unit delays. Okay, and in similar fashion, this part here, so this part here again it is running from n equal to 1 to capital N, which means that there is no scalar thing coming in picture. That will come when z to the power 0 we are having, and that term is here. So the delays will be contributed by all the n values which are located here. So in this particular part, n unit delays. Okay, so now here what we do is, in direct form 2, we realize this part and then we realize this part, right? So if we are doing that, then the number of delays or total number of delays . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . will be equal to m plus n. So what we have is, for feed forward, m delays, for feedback, n delays, which means for direct form 1, m plus n delays. Okay, so this we have. Now this we know. Now if in case the same question was asked for direct form 2, so right now what we are having is, we have our feedback. So let's say I denote it by A and I denote it by B. So first I have, or let's say just denote this as FF and denote this as FB. So here we first have, in direct form 1, we have feed forward, after that we have feedback, right? And in direct form 2, we interchange these two things. We make this here and this here. So we interchange this. So we have first feedback and then we have feed forward thing coming up. And here what we do is, we merge or we use same delays, same delay units as information is shared. And therefore, if I'm using same delays for both feedback and feed forward thing, and if feedback requires n delays and if feed forward requires m delays, and if I'm merging these two things and I require same number of or if I'm using the same delays, then I will use the number of delay units which is equal to the max of m and n. So therefore, for direct form 2, number of delay units is equal to max of m comma n. That you can see from any example which we have solved today. Any questions? Okay. If there are no questions, then let me move on to the 9th question today. So this question says that if y1 of z upon x of z is of the form of 1 plus az inverse into 1 plus bz inverse, then if a and b are real numbers with magnitude less than 1, then the values of k1 and k2 also have magnitude less than 1. True or false? So this is the question that we are having here. Now if you look carefully at this SFG or signal flow graph that is given to us. So this point is x, this point is x, this point is z inverse into x, this is also x. Then here at this location we are having this x getting added with z inverse into k1 into x. So here we are having x in plus x into k1 into z inverse. Then similarly at this particular location we have this k1 into x plus z inverse x. So we have k1x plus z inverse x here. So this we are having, and therefore now at this particular location we are having this y2 of z coming as it is, so that will be x plus x into k1 z inverse, plus I am having another branch which is this one. So at this location I am having this signal. So now I'll have the z inverse multiplied by this quantity multiplied by k2. So I'll have z inverse into k2 multiplied by k1x plus z inverse x. Okay, so therefore y1 of z will be equal to x of z plus x of z into k1 into z inverse plus k2 z inverse multiplied by k1 x of z plus z inverse z inverse into x of z. So now I can write this as y of z or y1 of z upon x of z as 1 plus k1 z inverse plus k2 z inverse. Inside the bracket I have k1 plus z inverse. I can simplify it as 1 plus k1 z inverse plus k1 k2 z inverse plus k2 into z to the power minus 2, which I can write as 1 plus k1 into 1 plus k2 z inverse plus k2 z to the power minus 2. Now what is given to us is y1 of z upon x of z yeah. So these take value of 1 plus az inverse into 1 plus bz inverse, and this if I simplify this becomes 1 plus a plus bz inverse plus abz inverse, sorry, z to the power minus. Okay, so now if I compare these two, compare this and this, so let me number it. So this is my equation 1 and this is my equation 2. So comparing one and two, we have a plus b equal to k1 into 1 plus k2 and ab equal to k2. Okay, so this we have. Now we know that magnitude of a and and magnitude of b both are less than 1, which means that k2 mag sorry magnitude of k2 is less than 1. Okay, now we have a plus b is equal to k1 into 1 plus k2 here. Then I can write this as k1 equal to a plus b upon 1 plus k2. So now this k2 can take maximum value as 1 or close to 1. So the denominator can be at most 2, and in similar way this numerator can also be at most 2. So equivalently this k1 will also be, or rather this magnitude of k1 will also be less than a plus, sorry, less than 1. For checking, you can just try the extreme cases and just substitute the values and check for all the values of a and b. So this I can also write as like this, and if we are having this particular form, this k1 will have magnitude less than 1 for a and b having magnitudes less than 1, and a and b being real quantities. So if you try and check for these values, you can figure out it in a better way. Okay, so this means that both k1 and k2 are having magnitude less than 1. So this particular thing here is true. Okay, so I had also plotted this particular thing for you people. So this a will take a value from -1 to 1. So this is my a, and my b will take a value from -1 to 1. So this is also b. And then I plotted this f function from for these values of a and b. And if you observe that the lowest value that it can take is -1 and the highest value it can take is 1, which means that this particular plot or this particular values like in the range of -1 to 1. So this figure is self-explanatory. So f max is 1, f min is 1. So here f is basically k1. Sorry, I should have written k1. So this k1 belongs to -1 to 1, which means magnitude of k1 will be less than 1. Just a short visualization because this is a little bit weird expression and drawing by hands is a bit difficult, so that's why I plotted it for you. Okay, so now let me just quickly move on to the next question. If you have any queries, then let me know. Otherwise, I'll move on here. So this is an extension to the same previous question which I just covered. So now here it says that now we are given the values of y1 of z and x of z, and it says that y1 of z upon x of z is equal to 1 plus 2.5 z inverse plus 0.5 z to the power -2, and we need to find the values of k1 and k2. So now if you remember, or rather if you look at whatever relation we had obtained, so we have this thing here, y1 of z upon x of z in terms of k1 and k2. So y1 of z, or rather from previous question, equation 1, y1 of z upon x of z was equal to 1 plus k1 into 1 plus k2 z inverse plus k2 z to the power -2. Now comparing it with given equation which is y1 of z, so I'll just write it here only, y1 of z upon x of z, which is given as 1 plus 2.5 z inverse plus k2, 0.5 z to the power minus 2. So if I compare it with the standard equation which we had obtained in the previous question, so now what we have is, therefore, k1 into 1 plus k2, so this thing here is equal to 2.5, and this thing here, k2, is equal to 0.5. So we have the value of k2, and now we'll just substitute this value of k2 here. So therefore we have k1 as 2.5 upon 1 plus k2, which is 2.5 upon 1 plus 0.5, which is equal to 2.5 upon 1.5, and this comes out to be equal to 5 by 3. So therefore k1 is 5 by 3 and k2 is 0.5 or 1 by 2. This is the final answer for this particular question. Any questions in this particular part? This was the last question that I had planned to cover today. If you have any queries in this question or in any previous questions which we did today, then please let me know. Yes, sir.
Madam, if it is a third degree expression, how this K1, K2 polynomial will be coming?
Sorry?
You gave the second degree expression, no? Z to the power of minus 2, h of z.
Huh.
H of z, second degree,
Huh.
you got K1 into 1 plus K2 like this, no?
Huh.
If it is third degree,
Huh.
if it is third degree, how the equation can be extended?
Sir, this is lattice kind of structure. Just wait for this particular week.
I see.
Yeah.
I see.
So this has nothing to do with the lattice and other things. This is just an SFG. Now you just wait for this particular week's content. You will understand how these things work.
Sorry, madam. I don't want to pinch off you. Just any extension idea, any extension.
Sir, if it is a third degree thing, then the question will be set in such a way that the number of unknowns will be equal to the number of equations that you will get. And so 3 equations, 3 unknowns. So you can solve the simultaneous equations.
So there is no polynomial rule for this.
No common
okay,
rule.
Okay, understood. Thank you, madam.
Yeah. Any other questions? If there are no further questions, then you're free to leave the meeting. Thank you for attending today's session.